Hello everyone, welcome back to VCodes. This is Vipin. Today I am doing this video as an extension of our last video, which was a digital clock. In that video we had created a digital clock module which had a clock input, a reset input and three standard logic inputs via which we could increment seconds, minutes or hours. And also we had three unsigned outputs respectively for seconds, minutes and hours, right? So in this project I want to extend the previous project by including a unsigned to BCD converter and a BCD to 7-segment decoder, right? So this will help us in testing this code on FPGA boards which have 7-segment displays in them. The outputs of this new module we are going to create assume that you have 6 7-segment displays not sharing a common bus. In case you have just 2 7-segment displays and you want to show the time in a round robin fashion way or something like that, then of course you need to modify the existing code, right? So that is case by case issue which we are not going to discuss here. So let's discuss the top module of this new digital clock. So you can see that there is a clock input, a reset input, 3 standard logic signals which is used for incrementing seconds, minutes and hours, and we have 6 outputs which will be connected to 7-segment decoders. They are all like 7 bits each and 2 each for seconds, minutes and hours. Okay, if you look at the naming you can see that seconds underscore 7 segment 1, 7 segment 10. So 1 means this is the BCD digit corresponding to the 1th place, and this is the second BCD digit which stands for the 10th position, right? Like for example, if the current seconds is 34, 3 will come here and 4 will come here, right? So that's how it is. Now let's see how the module looks from inside. What are the sub components in this top module? So this is how the digital clock looks inside. We have a few components here. So you can see that the digital clock which we did in our last project add 3 outputs: hours, minutes and seconds. So each of these hours, minutes and seconds is connected to one binary to BCD converter. Alright, so you can see that 6 bits go in and 8 bits come out. 8 bits means 2 BCD digits, and each BCD digit have 4 bits each, right? So this conversion is happening like minutes is also going to another binary to BCD converter and 8-bit BCD comes out. Similarly seconds to here. Alright, and then I have created a function in this top module which will convert the BCD value into a 7-segment decoded value. That is done with these blocks. So you can see that the BCD out from this binary to BCD converter goes into this, right? Like only the LSB position goes here and the MSB position goes to another one, and again similarly you can see the minutes also going to binary to BCD converter, and then that is connected to 2 of these blocks, like one here, one here. So the LSB BCD digit will go here, the LSB digit will go here and it will display, the result will come out here, and the MSB digit will go here and the result will come out here. Similarly for seconds also same thing. So this is how our module looks like. Now let's go back to Xilinx ISE and look at the codes. So we have this binary to BCD converter here. Let's start with library declarations, and you can see that a 6-bit input, binary input as unsigned format, as an unsigned type, and we have the BCD out which is also declared as unsigned, which is 8 bits. 4 bits each for 2 digits. So one thing I want to mention is that there are many ways in which you can convert a binary to a BCD value. Okay, so one thing, if the number of binary numbers are very less, you can use a lookup table, of course, like in a case statement or something. Or if there are many digits, it's if the binary value is very high, then you can use something called a double algorithm. I have coded a function for this, and it's available in my post. I will share the link in the description. So we have two digits, right? So these two digits, suppose the digit is 43. So 43 will be divided by 10. So you will get 4.3. So we will take that decimal part 4 and you will multiply that by 10, you will get 40, right? And from the original number, which is 43, I will subtract this 40 and you will get 3. So this is one way to get the result. Division in VHDL is always a bit complicated. It takes much more resources than multiplication. So if we are dividing a number by a constant, then what we do is we take the reverse of that, we take the inverse of that, and then multiply it by that value. Okay, so that is why what I am doing here. I am declaring a constant 1 by 10, which is this. So this is the actual value in binary, equivalent to 1 by 10.1 is equal to this in binary, but we can't mention like 0.11 like that using unsigned type. So what I did is I just took this part and then presented it as a 16-bit unsigned value. And you have to note that there are 19 fractional parts here. So actually this number divided by 2 raised to 19 is the value 1 by 10. Okay, so just keep that in mind. What we are first doing here is I have declared a signal result divided by 10 is equal to binary underscore in, which is our input binary number, multiplied by 1 by 10. Okay, so the input binary number is 6 bit and 1 by 10 is 16 bit. So the result will be 6 plus 16, 22 bit. So the result div by 10 is declared as a 22-bit signal. So 21 down to 0. Okay, and as I said that this number has to be divided by 2 raised to 19. So in this 22-bit result, the LSB 19 bits are fractional part and the MSB 3 bits are decimal part. Okay, so that's what we are doing here. We are taking the MSB 3 bits and append a 0 to it and then assign to MSB underscore digit, which is assigned to the output here. That part of the BCD out is assigned as MSB digit. Okay, so we have the MSB part of the digit now, the 10th place we have. Now we want to find the LSB digit. So how do we do that? We subtract the product, which is 10 multiplied by MSB digit, from the input binary number. So convert the unsigned type to integer and subtract MSB digit, which is also converted to integer, multiplied by 10, and then convert the result. So convert this whole result into a 4-bit unsigned number and assign to BCD out. So now let's look at the top module of this whole design. So this is our top module. Again, we start with the library declarations, and we have the digital clock top module entity here. Most of the inputs remain same, just like until here it is same, and this part is new, but I already explained via the block diagram what these signals mean, right? So we have two components inside this sub components. We have a component called a digital clock, which is the same thing we designed in our last project, and this is the binary to BCD converter component, which I just explained, and this is the function to convert BCD to 7-segment decoder. Okay, so you have a 4-bit BCD input and we return an unsigned type output. So we declare a variable called segment 7 as a 7-bit unsigned value, and within a case statement I assign a value to segment 7. So you can see that For 0 this will be the code, for 1 this will be the code. There is no formula for this. It's just based on how the 7 segment display looks like, based on what panels should be lit on that particular display. So for that you can refer to this link. I had already written a code there, but it was not in function format, so I just modified it. So 0 to 1 is included here, and if it's more than 9 then it's not a number. In such a case, if it ever happens, you can assign the segment 7 as 1 1, which means nothing will be displayed on the display, right? So that's the function. And we have this internal signals, and now we instantiate the digital component, just like in our last project. And these are the binary to BCD components, where I pass seconds, minutes and hours to it. And you can see that hours I have used a different signal called hours extended, which is nothing but a 0 appended as the MSB part of hours, because seconds and minutes are 6 bits each and hours is only 5 bit. So before passing it to the module which expects a 6 bit input, I need to append a 0, okay, to the hours. So that's why I'm using hours extended here. Once that is done, we have the BCD outputs, and then I just pass all these BCD outputs, 6 digits. I'm passing it to this function BCD to segment 7. You can see that LSB digit, MSB, LSB digit, MSB digit, and so on, and each of these assigned to the respective outputs. So that's all about the digital clock top module. Now we want to test this thing, right? So let's go to the Testbench code. Testbench code is again similar, starting with the library declaration. This is used to finish or stop the simulation after we are done. So empty entity for the Testbench, the component which we are going to test, which is our digital clock top module, inputs, the internal variables of the Testbench, which are inputs and outputs to the design under test, clock period 10 nanosecond, and clock frequency is used as 10 in this case, just for testing purposes. So here we instantiate the unit under test. This is the clock generation part and the stimulus part. There is no change in this part compared to our last video. So I guess you could refer to that part if you don't understand something here. Okay, so that's all. What I'm gonna do is now just simulate the code just to show you how it's working. So let's zoom out, and I want to add some internal signals to this waveform. So how do I do that? I click on UUT. So these are the various internal components, subcomponents in this design. So I'm going to click on this top module UUT and add this seconds, minutes and hours to here, and I want to change the radix to unsigned decimal. Okay, and then I want to add the BCD seconds, BCD minutes and BCD hours, drag and drop here, and change the radix to hexadecimal because they are of BCD format, right? So I guess that's enough for now. Let's run this code for 10 millisecond, 10 ms. Click on this. You can see that for example here the minutes is 0, so it shows 0 0. Both LSB and MSB digits are 0, and 1 is 0 1. So just so that you know, these two numbers are not the same. This is a 6-bit unsigned number and this is 8-bit or 2-digit BCD number. Okay, so 3 is 0 3 and so on, 10 is 1 0, 11 is 1 1, and it goes like. You can verify in your own system that all the numbers are correctly being translated. So 59 59 is 59 and so on. So these seconds which are created by our digital clock module are passed to the binary to BCD converter and we get these, right? And this is passed to the function and we get these outputs, okay? So these outputs may not make any sense to you when you look in this way, but when you test it on a board, you can see the values on a 7-segment display. Look into the blog post for which I shared the link in the description, and you can see what these codes means and how we come up with these codes. So that's all in this video. I hope you liked it, and if you do, please like the video and subscribe to my channel and show some support so that I'm motivated to upload more such videos in the future. All right, thank you, bye bye.